Okay, in this podcast we're talking about spectroscopy. This is section 1.13. We have very little in the textbook on spectroscopy, so most of it you're going to have to learn from the podcast or looking at other sources online. Okay, so spectroscopy is simply learning about matter by interacting it with light. That's it. That's all it means. Whenever we do spectroscopy, there's always three pieces that need to be present. You need a source of light, you need some sample that you're evaluating, and you need a detector. When we do spectroscopy, we use it as an analytical technique. We use it to figure something out. Okay, we can do it as a qualitative technique, which means we're trying to figure out what is in our sample. Or we can use it as a quantitative technique, for instance, to figure out the concentration of a sample. In its simplest form, you can imagine looking at a red shirt is spectroscopy, because we have a source of light, be it the sun or lamp over in your bedroom. You have a sample, which in this case is the red shirt, and then you have a detector. Okay? So the light hits the shirt, it interacts with the shirt, some wavelengths of light come off, and that is what your eye detects. Okay, so let's just remember, we know about electromagnetic radiation. We use the term electromagnetic radiation and light interchangeably. We know that the speed of light is equal to the frequency times the wavelength. We know that the smaller the waves, the higher the frequency. We know that we have a whole range, and we can put them into categories. Big, long waves are radio waves. They're low in energy. Really high energetic waves are gamma rays. They are really little tiny wavelengths. And we've got the whole range in between. So what we want to do is talk about areas of the electromagnetic spectrum, and we're going to go to increasing energy. So this is the high energy down here, short wavelength, high energy, and talk about how these can be used analytically to do things that allow us to figure out stuff about matter. So first of all, microwave radiation is capable of causing molecules to rotate. Now, it turns out we don't use microwaves analytically in chemistry because they don't give us enough useful information. But what they can do is they can make molecules rotate or spin. So if you think about putting your food in the microwave, those molecules get energized, they move around, they spin, and that's what cooks your food. And eventually the water gets enough energy and it becomes a gas and it leaves, and that's what cooking is. Okay. Radiation, which is the next highest form of energy. We don't do anything to protect ourselves from infrared radiation. It can be used to cause molecules to vibrate or stretch. So we can use infrared to stretch covalent bonds, and based on that, either identify what type of bond a substance has, or if we have a mixture of stuff and we're trying to isolate something, we can identify, narrow down what we have. So you do need to know this. You do need to know that IR spectroscopy allows us to identify or distinguish different bond types. That's actually in one of the learning objectives for the curriculum this year, so you need to know that. Okay, visible light, we know, can be used to cause electronic transitions. Just visible light is enough to cause electrons to jump from their ground state to their excited state and to fall back to their ground state, releasing colored light. Right? That's how we see colored things. And the emission spectrum that comes out of that we can use to identify an element, because each element has its own unique emission spectrum. Okay. We can use visible to identify the color of an object, and we can also use visible light to help us figure out the concentration, and we're going to actually do a lab with that. All right, going up in energy, You know it's higher in energy. You know that we are told to wear sunscreen when we're outside. It will also cause these electronic transitions that cause electrons to be energized. But it also involves some ionization. And what I mean by that is if I have an element, let's just call it element A, and I give it some energy, it causes that to become a positive ion and it loses an electron. It became an ion. It's become ionized. And in fact, this process, which is oversimplified here, this ionization process is why you have to wear sunscreen. The process of UV, some of the UV is strong enough that it can force electrons off and form, when we talk about it biologically, we often talk about free radicals. And these are things, once they become ions in your body, that can cause changes in cells, and therefore you can end up with things like cancer. Okay, X-ray radiation. We know X-rays are harmful. You know, if you've ever gone for an X-ray, that you had to wear a lead vest to protect yourself, so it's got to be pretty nasty stuff. And, X-rays lead to ionizing radiation. And again, just like we said with some of the more harmful UV, you can cause these ions or free radicals to form, which of course can lead to cancer. We can use electron configuration analytically. We can use X-rays analytically to identify electron configurations. We saw that with PES, where we can get some really good data about the binding energy or how many electrons something has by evaluating it with a photoelectron spectroscopy. Now, we don't typically use gamma rays because gamma rays most usually come off of nuclear reactors, and they will change the nucleus. Really fundamental change, produce lots of energy, cause cancer, all that other stuff. But so these are the ones that we typically think about when we think about using them, taking advantage of them to figure stuff out in chemistry. All right, we're going to